A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. You ever have those moments where your technology feels less like a marvel of engineering and more like a collection of haunted artifacts? I'm talking about the weird glitches that make no sense. You turn off a desk lamp and your computer monitor flickers, or you hear a strange buzzing in your speakers right before your phone receives a text message. It feels like ghosts in the machine, but it's actually just physics being messy.
It is the invisible chaos of the world, Corn. We live in a soup of electromagnetic radiation, and honestly, it's a miracle anything works at all. I'm Herman Poppleberry, and today we are diving into the hidden wars happening inside your circuit boards.
Today's prompt from Daniel is about electromagnetic interference, or EMI, and the high-stakes world of electrical shielding. Daniel actually mentioned a classic ghost in the machine scenario he's been dealing with at home. He has a 3-monitor setup, and occasionally, when he turns off just one monitor, the other two, or even the whole set, decide to take a nap too. It's that classic crosstalk where one device's off signal becomes another device's everything is broken signal.
That is such a perfect example of what we're talking about today. And by the way, for those curious about the technical side of the show itself, today's episode is powered by Google Gemini 3 Flash. It's helping us navigate this electromagnetic soup. But back to Daniel's monitors. That's EMI in a nutshell. It's unwanted electromagnetic radiation disrupting the intended operation of a circuit. You've got a source, a path, and a victim. In Daniel's case, the source is likely the power switching or the signal handshake of that first monitor. The path is the cables or even just the air between them, and the victims are the other two screens.
It's funny because we spend so much time worrying about software bugs or hardware failures, but we rarely think about the fact that electrons are just incredibly social. They don't like staying in their own lanes. They want to jump over to the neighbor's wire and start a party.
They really do. And as we pack more and more electronics into smaller spaces, think about your phone, which is basically a high-powered radio station, a computer, and a high-resolution camera all crushed into a glass sandwich. The internal screaming of those components becomes a massive engineering hurdle. If we didn't have shielding, your Wi-Fi chip would basically drown out your Bluetooth connection, and your cellular modem would probably fry your camera's image sensor before you could even take a selfie.
So, before we get into the heavy physics, let's frame the scope here. We're talking about everything from the hum in an old guitar amp to why your airplane mode exists, all the way up to how we stop electric vehicles from jamming their own GPS. It's a massive topic.
It is. And it starts with understanding that every time electricity flows through a wire, it creates a magnetic field. And every time a magnetic field moves past a wire, it creates electricity. That's Maxwell's equations in action. It's beautiful on paper, but in a crowded apartment or a modern car, it's a nightmare.
Okay, so let's break down the why here. Why is this happening more now? I don't remember my Game Boy interfering with my TV back in the 90s.
Well, part of it is frequency. Back then, we were working with much lower clock speeds, but today, we are pushing gigahertz signals through everything. The higher the frequency, the easier it is for that energy to radiate out like a radio wave. Plus, our devices are way more sensitive now. We are trying to detect tiny, tiny fluctuations in voltage, and when a stray electromagnetic wave from your microwave hits that line, it looks like a signal to the processor.
It's like trying to have a whispered conversation in the middle of a heavy metal concert.
Or, well, it's exactly like that, but with the added complication that the heavy metal band is literally inside your head. When we talk about EMI, we usually categorize it into two types, conducted and radiated. Conducted EMI travels through the physical wires, like a noisy power supply sending trash electricity into your PC. Radiated EMI travels through the air as electromagnetic waves.
And that's where the shielding comes in. The security fence for electrons, as you put it earlier.
Right. Shielding is our primary defense. It's usually a conductive or magnetic barrier that wraps around the sensitive bits. And it works through three main mechanisms: reflection, absorption, and grounding. When an EMI wave hits a metal shield, most of it just bounces off. That's reflection. The metal acts like a mirror for radio waves. Some of the energy that doesn't bounce off gets soaked up by the material and turned into a tiny amount of heat that's absorption. And finally, any charge that builds up on the shield needs a place to go, which is why we ground the shield so the noise can be drained away safely to the earth or the chassis.
I love the idea of draining noise. It makes it sound like we're plumbing for electrons. But I imagine this isn't as simple as just wrapping everything in tinfoil and calling it a day, right? Otherwise, Daniel wouldn't be having monitor issues.
If only it were that easy. Tinfoil is a start, but the engineering trade-offs are brutal. First, you have the skin effect. As frequencies get higher, the electricity doesn't travel through the whole wire. It only travels on the very outer surface, the skin. This means your shielding needs to be designed specifically for the frequencies you're trying to block. If you're dealing with 5G or millimeter waves, a standard piece of aluminum might not cut it. You might need specialized sprayable conductive coatings or even exotic materials like MZenes, these ultra-thin 2D materials that are being developed right now.
And then there's the weight and cost. If you're building a satellite or an electric plane, you can't just lead line the whole thing. You'd never leave the ground.
Precisely. And don't forget thermal management. If you wrap a high-powered processor in a solid metal box to stop EMI, you've also created a very effective oven. You're trapping all that heat inside. So engineers have to design shields with holes in them. Perforations that are small enough to block the electromagnetic waves, but large enough to let air circulate. There's a whole branch of math dedicated to calculating exactly how big those holes can be before the leaks become a problem.
It's like trying to build a cage that keeps out mosquitoes, but lets in the breeze.
That's a great way to put it. And it gets even more complicated when you consider the apertures, the places where cables enter the shield. Every time you poke a hole in a shield to run a power cord or HDMI cable, you're creating an entry point for EMI. This is why high-end cables have those little plastic bumps on them. The ferrite beads. Those are actually magnetic chokes that eat high-frequency noise before it can enter the device.
I always wondered what those little lumps were. I thought they were just there to make the cable look more pro.
They are essentially tiny EMI filters. They turn the unwanted high-frequency energy into heat. It's a passive way to clean up the signal. But let's look at a real-world disaster of shielding design. Antenna gate with the iPhone 4. Remember that?
Oh, I remember. You're holding it wrong.
Right. Steve Jobs' famous line. The issue there was that Apple tried to use the outer metal band of the phone as the antenna. It was a beautiful design, but they didn't account for the fact that a human hand is a conductive bridge. When you touched a specific part of the band, you were essentially shorting the antenna to the rest of the internal shielding, which killed the signal. It was a classic case of an engineering trade-off. Aesthetic versus aesthetic versus aesthetic. Electromagnetic reality, going sideways.
It's funny how these invisible forces can bring down a multi-billion-dollar product launch. But let's talk about something even more high stakes. Electric vehicles. You mentioned they are massive EMI generators. Why is that? My old gas car had an alternator and spark plugs, which I assume made some noise, but EVs are a whole different beast.
It's the sheer scale of the power. In an EV, you have a massive battery pack sending hundreds of volts to an inverter, which then switches that power on and off thousands of times a second to drive the motor. That high-speed switching is like a giant megaphone for EMI. It creates massive amounts of noise that can interfere with the car's AM radio, which is why many EVs don't even offer AM radio anymore. But more importantly, it can mess with the sensors.
Like the LiDAR or the cameras for autonomous driving.
Imagine your self-driving car gets blinded, not by light, but by the electromagnetic scream of its own power steering motor. There were reports back in 2023 about Tesla Model 3 infotainment systems having glitches that were eventually traced back to EMI issues. Engineers are constantly battling to isolate the high voltage side of the car from the sensitive data side. They use heavy-duty shielded orange cables. That's why they're orange, by the way, to signify high voltage and shielding. And they basically build Faraday cages around the motor controllers.
It sounds like a constant game of whack-a-mole. You fix the noise in one spot, and it just pops up somewhere else.
It really is. And the stakes are even higher in medical devices. Think about a pacemaker. It's a tiny computer sitting inside a human body, looking for the very faint electrical signal of a heartbeat. If that pacemaker picks up EMI from, say, a wireless charger or a powerful motor, it might think the heart is beating when it isn't, or vice versa. That's why medical shielding is so ultra-conservative. They use titanium housings and specialized feed-throughs that are tested to extreme levels.
I actually read about a 2023 study from the IEEE that found 30% of IoT device failures in industrial settings were traced back to EMI. 30%! That's huge. It's not that the software crashed or the battery died. It was just that the environment was too noisy for the device to think straight.
That's the noise floor problem. As we add more devices, the overall level of background electromagnetic noise in our cities is rising. It's like trying to live in a house where everyone is constantly shouting. Eventually, you just can't hear anything. This is why the FCC and other regulatory bodies are so strict about Part 15 compliance. Every electronic device sold has to prove it doesn't emit too much trash and that it can handle a certain amount of incoming trash without breaking.
So, if you're Daniel, and your monitors are acting up, or you're an audio engineer dealing with a hiss in your signal, what do you actually do? How do you fight back against the invisible screaming?
Well, the first step is always identifying the path. In audio engineering, the most common culprit is the ground loop. This happens when two pieces of equipment are connected to each other but are also plugged into different power outlets. They end up having slightly different ground levels, and that difference creates a current that flows through the audio cable itself. That's the classic 60 Hz hum you hear.
And the fix for that is usually a ground lift or a balanced cable, right?
Yes, balanced cables are a brilliant bit of engineering. Instead of just one signal wire, you have two. One carries the signal, and the other carries the exact same signal but inverted, upside down. When the cable picks up EMI along its length, the noise hits both wires equally. At the other end, the device flips the inverted signal back over and adds them together. The original signal gets stronger, but the noise, which was the same on both, cancels itself out. It's like mathematical magic.
I love that. It's essentially anti-noise. But what about Daniel's monitor problem? That sounds more like a power surge or a poorly shielded HDMI cable.
It could be a few things. High-quality HDMI cables have internal shielding for a reason. If you use a cheap unshielded cable for a high-resolution, high-refresh rate monitor, you're basically running a giant antenna across your desk. When one monitor switches off, it might send a voltage spike or a signal reset back down the line, and if the other cables aren't shielded, they pick up that hiccup, and the monitors lose their handshake.
So the takeaway for Daniel is, buy better cables and maybe a better power conditioner.
Usually, yes. A power conditioner or a high-quality surge protector with EMI filtering can make a huge difference. It acts as a gatekeeper for your power, smoothing out the dirty electricity before it hits your sensitive gear. And for the cabling, look for triple shielded or braided shields. It's one of those rare cases where the expensive cable might actually be doing something useful, rather than just being a marketing gimmick.
It's rare we give the buy the more expensive cable advice, but when it comes to high-speed data and EMI, it's legit. Now, let's look toward the future. We mentioned 5G and 6G, but what about things like graphene or carbon nanotubes? Is that the future of shielding?
We are reaching the physical limits of traditional copper and aluminum. As we move towards 6G, which will operate at even higher frequencies, up into the terahertz range, traditional metal shields start to act more like antennas than barriers. We need materials that can absorb that energy rather than just reflecting it. There is a huge push right now for sustainable shielding. Using bio-based carbon materials, like charcoal-derived graphene, which is light, flexible, and much easier to recycle than heavy metals.
I like the idea of green shielding. It's funny to think that the future of high-tech 6G phones might involve a material made from charcoal.
It's a full circle. But the real challenge is going to be miniaturization. We are putting more and more power into smaller and smaller chips. We're getting to a point where we might need on-chip shielding, literally building the Faraday cage directly onto the silicon. There's a technique called conformal coating, where they spray a microscopic layer of conductive material over individual components on the circuit board.
It's like giving each chip its own little suit of armor.
Precisely. And that armor has to be perfect. Even a tiny crack in the coating can let in enough EMI to cause a failure. This becomes critical in things like quantum computing. Quantum bits or qubits are incredibly fragile. They can be knocked out of their quantum state by a single stray photon. To build a functional quantum computer, you basically have to build the most perfectly shielded room in human history. We're talking multiple layers of superconducting shields, vacuum chambers, and absolute zero temperatures just to keep the electromagnetic noise out.
It makes my desk setup feel very robust by comparison. But it's a good reminder that as we push the boundaries of what's possible in computing, we're also pushing the boundaries of how we isolate ourselves from the universe's background noise.
It's a constant battle between our desire for connectivity and the laws of physics. We want everything to talk to everything else. Our watch to our phone, our car to the city, our fridge to the grocery store, but every one of those connections is a potential source of interference. The Internet of Things is basically the Internet of EMI sources, if we aren't careful.
I think that's a great place to pivot to some practical takeaways for the listeners. Because most of us aren't building quantum computers, but we are all dealing with weird tech glitches.
Right. Number one, if you're troubleshooting a mysterious glitch, look for the source, path, victim trio. If your speakers are buzzing, is there a router nearby? Is the audio cable crossing over a power cord? Try to separate your power cables from your data cables. If they have to cross, make them cross at a 90-degree angle. That minimizes the area where they can interfere with each other.
That's a pro tip right there. The cross at 90 degrees rule. It sounds like superstition, but it's pure geometry.
It really works. Another one for the hobbyists out there, if you're building a PC or a DIY electronics project, don't ignore the grounding. Make sure your motherboard is properly seated on its standoffs and that your case is grounded. That metal box isn't just for looks, it's a Faraday cage designed to keep the scream of your CPU inside. If you leave the side panel off, you're not just potentially letting dust in, you're letting EMI out.
And if you're really stumped, you can always use the AM radio trick.
Oh, I love this one. If you have an old portable AM radio, turn it to a frequency where there's no station, just static. Then move it around your electronics. You'll hear the static change or buzz when you get close to a source of EMI. It's a great cheap way to hunt down noisy power bricks or poorly shielded devices. It's like a Geiger counter for electronic noise.
I used to do that as a kid and thought I was detecting aliens. Turns out it was just the back of the refrigerator.
Hey, to a kid, a compressor motor is basically an alien, but it's a valid diagnostic tool. And lastly, for anyone buying gear, look for those ferrite beads. If a device comes with a cable that has one of those lumps, use that specific cable. Don't swap it out for a cleaner, looking one you found in a drawer. That lump is there for a reason.
It's funny how much of our modern world relies on these invisible fences. We take it for granted that our phones work while we're charging them, or that our cars don't stall when we turn on the radio. But behind every one of those non-events is an engineer who spent weeks worrying about the thickness of a copper foil or the placement of a grounding pin.
It's the unsung hero of the digital age. Without shielding, the information superhighway would just be a massive electrified pileup.
Well, I think we've successfully unmasked the ghosts in Daniel's monitors. It's not a haunting, Daniel. It's just Maxwell's equations being a bit too enthusiastic.
Or, well, not exactly, but you've got the right idea. It's the physics of the soup we live in.
I was waiting for you to say it. You almost made it the whole episode without the E word.
I'm trying, Corn. I'm trying to be more descriptive. But you're right, it's the fundamental reality of how electrons behave. They're messy, they're social, and they don't like being told where to go.
Well, this has been a fascinating deep dive. I'm going to go home and check all my cables for ferrite beads now.
Just don't start wrapping your whole house in tinfoil. Your neighbors might start asking questions.
No promises. I think a tinfoil hat might actually improve my Wi-Fi reception if I angle it right.
Please don't test that theory.
Too late. The plans are already drawn up. Anyway, that's our look into the invisible world of EMI. A huge thanks to our producer, Hilbert Flumingtop, for keeping our signals clear.
And a big thanks to Madal for providing the GPU credits that power this show and keep our scripts flowing.
This has been My Weird Prompts. If you're enjoying the show, maybe leave us a review on your favorite podcast app. It helps us reach more people who might be wondering why their monitors are possessed.
You can also find us at myweirdprompts.com for the full archive and all the technical deep dives.
See you next time.
Stay shielded.
This episode was produced using Google Gemini 3 Flash, text-to-speech by Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow